Okay, this is Dr. Morton, and so this is the video I promised for Friday, and so hopefully you're viewing this on Friday, and so what I'm going to do, I'm going to cover the traffic light thing. So let me do this. Let me shrink myself down a little bit, and I'll pull myself over here. And then I want to raise up this. So here's the textbook, and one of the things I did in chapter 12 in the text, and I'd like you to read this. I did go through this traffic light thing. I did this partly because this has traditionally been used in the logic design lab, and students are always panicked over it and usually come to me for help, even though I don't usually teach. I've never taught the logic design laboratory, but I get drug into it. So I thought I'd just go ahead and cover it in the course, and would make life easier for students in logic design lab. All right, so this is a little bit tricky, just because of the size, but there are ways to make it easier, which we'll eventually get around to covering. So if hopefully you've read through this part. This is kind of the quintessential example of sequential design, and so anyway, so there it is, and here's the truth table, which is actually a little bit hard to read in this format. All right, so I'm going to shrink this down. So this traffic light is really a perfect example of a state machine. This is exactly how a state machine works, right? You get since you've sat through Lord knows how many stoplights in your life, me too. You're very aware of this idea that the stoplight goes through a fairly standard sequence of events, right? And it repeats it over and over and over again. Now, obviously, stoplights have gotten a lot more complicated as time has gone on, and now we have sensors, and the sensors have gotten more complicated. You probably have noticed that many of the intersections now have cameras that they use for the sensors, rather than the little buried in the in the early days. The very first sensors were rubber sensors. They were big, thick rubber pads with kind of switches underneath, and these would break pretty frequently. So here are a couple of examples of that. You can see here we have they'll use a concrete saw and saw a little groove, and they'll drop a loop of wire in, maybe even in a couple of places across the lanes, and they'll run these back to a controller box that will inductively sense the presence of a bunch of steel in the form of an automobile or a truck on top of this loop. Lately, in the last 20 years, we've had a real advent of cameras, and it turns out if you talk to people that install these things, you'll see that the cameras look like they're a lot easier to install, and I think that's probably true because you don't have to saw up the pavement and stop traffic and everything. But they both have problems. And the ones that are embedded in the concrete, when temperatures shift, especially in northern states where it freezes and thaws, there'll be enough shifting here that it'll cut the loops, the wires will break, or just the sheer pressure of traffic moving over will eventually cause a break in the wire, and then the sensor stops to function. Now you've got to go out and dig this up and lay new wire in it, and that's a super hassle. So the cameras, on the other hand, on funny weather changes, sun shining right in the face of the camera, a number of features can cause them to stop working, and then certain colors cars they might miss. I mean, they're susceptible to problems. There can be just condensation on the camera lens if it's a super humid day or the temperature changes quickly. So there's a lot of things that can happen, and as a result, they both have problems, and they're almost equally expensive when it's all said and done. So, but you do see more and more stoplights featuring the camera system and no sensors in the road. And one nice feature is these can cover a wider area depending on where you place them. And they can also see as cars approach. So if for some reason the car's not quite on the sensor, you may not trigger the light. That can be very frustrating, especially if you can't tell exactly where the sensor is. And but the camera may make up for that by having a little wider field of view. So anyway, so that's kind of part of the kind of some of the sensor based. So you've all seen the standard intersection where in this case we don't really have a sensor. What we have is just a basic stoplight. In this case now, for the most part, you would only have to control east-west traffic and north-south traffic. So let's say the north-south lane is the main lane and the east-west lane is a less busy lane. So in this case, we'd probably put this on a fixed timer, assuming we didn't have any sensors connected to it, and we would maybe let the north-south traffic go for maybe a minute or 50 seconds, and then we'd give 20 seconds for east-west flow, or depends on how heavy the traffic is. You might even have it change based on the time of day and things like that. But in any event, we're just going to model this with 50 seconds north-south, and then 20 seconds east-west. 50 seconds north-south, 20 seconds east-west. And in between those transitions, we have to have a state where we continue to give a red light for, say, the east-west traffic, but we give a yellow light for the north-south before we switch it to green for east-west and then red for north-south. And you have to maybe give a 10-second yellow time, or maybe a little less. Okay, so if you then want to design a state machine to do this, then there's a couple things you have to do. And no, in this case, no left turn arrows involved, no sensors, okay? So here's a state graph that basically lays this out. Now the way this works, each state, so we have a clock that's going to switch us from each state. There's no inputs, and there are a bunch of outputs. The outputs are the traffic lights, and so we have, in this case, since we're always going to have the north-south traffic flowing or the east-west traffic flowing, we only have to have control 3 different lights for north-south and 3 different lights for east-west. So we have 6 outputs in this particular arrangement. And we start in S0. We have a yellow light for the north-south, and the clock is set up so each state is 5 seconds. So the clock ticks with a 5-second period. So 5 seconds we're in state S0, and then tick, we immediately go to S1. We're still yellow for north-south, red for east-west. Tick. Now we're green for north-south. Green for east-west, red for north-south. And then we tick 1, 2, 3, 4, 5 more times, or 5 total times. So 6 times. So 30 seconds. Yeah, I guess we did 30 seconds here. So 30 seconds for our east-west traffic. And then we have yellow for 10 seconds, 5 seconds here, 5 seconds there, where north-south is still red. And then we turn north-south green, and we make east-west go red. And so then we're green, north-south for 5, 10, 15, 20, 25, 30, 35, 40, 45, 50 seconds. And then we go back up here, and again we have 10 seconds of north-south yellow, east-west red, and then we have 30 seconds of east-west green, north-south red, then yellow for the east-west, and then green for north-south, and we repeat that. So that's how this works. Okay, and so if we start in state S0, we have red for a side street and yellow for the main, and then we repeat to give 10 seconds of yellow, and then the green side street and red for main, and we do that 5 more times for a total of 30 seconds. Then our next yellow for our side street and red for the main, and then green for the main and red for the side street, and we do that then 9 more times for 50 seconds, and then we go back to S0. Okay, so this is how this works. Oops. So we have 20 states, 6 outputs, no inputs except for the clock. Okay. Yeah. Okay. Now, what we're going to do here, we're going to add a sensor. And we're going to create a left turn lane in the northbound lane, not in the southbound lane. Now, what this complicates things because now we have an arrow output and a green light, yellow light, red light for northbound, and then for southbound we just have a red, yellow, and green, or maybe actually this is southbound, red, yellow, green. So, but we can have we have to separate out now. We have to have different controls for the northbound green and red than we do for the southbound green and red. We can leave the yellow the same. Okay, so what we do then, when we're going to have to modify our state graph, and now we have an input. Before the only input we had was the clock. Now we have an input, and so we put in this little cutout here, and we have an input x, and if x equals 1, then that means the car is present on the sensor. So right now we have east-west traffic, then we go yellow for east-west, yellow for east-west, and then in our last east-west yellow state, we before we go to the next state, we check x, and if x is 1, then we're going to go down here to 9A and then later on to 9B, and that's going to give 10 seconds of left turn arrow. And then we go to S10. Turn off the left turn arrow, and now we're just green for east-west, and we do that for 50 seconds like we did before. Now, if, on the other hand, we get to S9 and our sensor is 0, x prime, then we just go straight on to S10. And we never have the green light. Now I didn't put in here, but you also have to make sure that the southbound light stays red. You can't let it turn to green, otherwise you're going to hit your left turning cars. Probably should put that in somewhere. Okay. So this adds. So we had 20 nodes. So now we have 20. So now we had 20 nodes. Now we have 21 and 22 nodes. Yeah, I think I may have messed this up, but anyway. Okay, all right. So now, and you only check the sensor when you're in S9. That's the only time you really look at it. The rest of the time you ignore X, regardless of whether X is 1 or 0. You're going to the next state. Okay, now here are the unique lights we have to control. We have to control the east-west red, east-west yellow, east-west green. We have to control the south red, the south green, and then we can control the north-south yellow. Can all be one light. They can always, when the north is yellow, the south will be yellow too. And then we'll separate out the north red and the north green and the north left arrow. So we have 9 unique lights that we have to control, 9 outputs. So here's our truth table, or I should say our state table. Our state table has we have 19 states plus 9A and 9B, so 20 and 21 states. Oh, it's actually 21 and 22 states. Yeah, 22 states, 9 outputs. So we're going to need 5 flip-flops, which will give us, we could have 32 states, but we're only going to use 22 of them. So we're going to have some don't cares. And then here are our 9 outputs. East-west red, east-west yellow, east-west green, south red, south green, north-south yellow, north red, north green, north left arrow. Okay, so we're gonna see if we can generate the K-maps for this problem. Now, it turns out, I'm not going to do them all because this is a bit of a mess. So first off, what are our independent variables? Well, our independent variables are X, A, B, C, D, and E. We have to have 5 flip-flops to cover our 22 states. We use straight binary encoding for A, B, C, D, E for the states, and so therefore S0 would be A prime, B prime, C prime, D prime, E prime, and so forth. S1 would be A prime, B prime, C prime, D prime, E, and continue. And S22 through S31 are don't cares. And actually, I think 19, 20, 20, right, that's right. S22 and to S31 are don't cares. And then 9A and 9B we'll rename and we'll call those S20 and S21. Okay, yeah, that looks correct. All right, so here's our truth table. Now, how are we going to do this? Well, it's a little bit challenging for sure. But for starters, this is pretty messy because we have a lot of flip-flops. And so for the flip-flops, we need the independent variables. And that includes, for our flip-flop inputs, we have to have X, A, B, C, D, and E. So we'll need 6 variable K-maps. So we would have to have 5 6 variable K-maps. And then for the 9 outputs, we only need A, B, C, D, E. We don't need X because the outputs, these are more outputs. They only depend on the current state that we're in. So, and our current state is always defined by A, B, C, D, E. The X doesn't define what state we're in. It just potentially changes the next state that we're going to go to. In this problem, it only impacts one node. That's it. And all the other nodes then are not impacted. So it's not terrible, but it's still challenging. So for a Moore machine, the outputs depend only on the current state, and so we need 5 variable K-maps for the 9 outputs, but we need 6 variable maps for the flip-flop D inputs. So for DA, DB, DC, DD, and DE, we need a 6 variable K-map for each one of those. So I'm going to do the outputs with a 5 variable map, and then I'll do one input. Well, I'm only going to do one output. I'm only going to do one input, just because they're somewhat complicated. All right. So here's the example map. This is for the east-west red output. Okay. So if we go back and look at it here, sorry. So here's our east-west red. So there's 1, 2 up here, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 different. We should have 14 different ones when the east red light is 1. Now where we have a 1, that means the light is on. And everywhere where it's a blank, it's really a 0, and that means the light's off. Okay? Now, so here's the K-map. Let's see, did we do that? Yeah, so here's the K-map. So the way we're doing this, remember, we're doing 5 variable maps. So this map is, the axes are going to be B, C, D, E, and this 4 variable map is where A equals 0. That's our 5th variable. And this map is where A equals 1. Now if you notice, we put our don't cares in here, and then we put in the 1s. Now it turns out A is a little bit easier because it's the hierarchical variable, so it's only 1 once you get past state 16. All right, so anyway, so this makes it a little bit easier. And then, yeah. So this map turns out to be the constant 1, or A, actually, the constant. So it's A, because this is A0, and this is A1. So this map isn't the constant 1 because over here you have where A is A prime. So you haven't eliminated A. This is just A. And then, so we group this all like this. Then, because this row of 4 can be grouped with this row of 4, we get a group of 8, and that's going to be BC. The big loop over here is just A, then BC. Then we group these 2 groups of 4 for a group of 8. That's BD. And then we have 2 here with 2 there for a group of 4, and that's B prime, C prime, D. Now, obviously, because these show up on both the A equals 0 and A equals 1 map, the A is going to drop in these 3. But because this is just the one map and it's in every single position, either a don't care or 1, then it's the variable A. All right. And So remember, again, because this is a Moore machine, X does not show up in the output equations directly. Of course, it affects it indirectly, but really only in one node. Now here's our DA flip-flop. Oh, I should have fixed this. Anyway, what's interesting about this is these are all zeros except there's a 1 here. And these are all 1s. And so we can definitely, so the don't cares don't depend on the variable x. They only depend on A, B, C, D, E, since they're related to the states. And for x equals 1 and x equals 0, the only state where there will be any different next states is state 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this one right there. And when x is a 0, then state 9 here goes to just the next state of 10. But when x is 1, there'll be a 1 here, and so it's going to go to a different next state. And so the way this works then, our x drops out of this map. These can be grouped well here. So since we're doing the DA input, it's pretty easy to put in the rest of the ones. Okay, so we did that. We group all of this together, and we get A. Okay? A is 1 here, A is 1 there, X is 0 here, X is 0 here, and all the other things grouped together. So we wind up with the only variable here from our 6 variables is A. So that's A plus, and then we group this one with that one there. And that gives us X, B, C prime, D, E prime. The only variable that drops is our A. The A variable is 0 here and 1 here, so the A drops. So we have A plus X, B, C prime, D, E prime. And that's the solution for the DA input. So we'll see later on, we'll take a look at this problem again, and we'll show that if we use an SM chart, it's going to be a lot easier to solve this one, because 6 variable K-maps are very difficult and challenging. Okay, so that's pretty much what I wanted to cover. Make myself bigger here. Okay, so hopefully that'll give you a little bit of a feel for this traffic light problem. I did want to cover that. I want you to read through that in the book as well, and hopefully you'll start to see this is an example of something close to a row. I mean, there are stoplights out there that work like this, but most of them are a little more complicated. And they also have features where when there's a power failure and they come back on, for some reason they go into flash mode. I've never understood that. They could just as easily pick back up where they left off. I don't know why they go into flash mode when the power cycles like that. I've never understood that. Some of them have sensors to pick up emergency vehicle lights, and that causes it to go and to turn all red, so it stops all the traffic and it lets the emergency vehicle get through the intersection with less risk. And there are clearly other things. Some of them have input from pedestrian to walk buttons, and if the button's pushed, then when it cycles to that point, it'll stop all traffic and let the pedestrians cross. Sometimes, in some cases, in other cases, they let the traffic continue to go, but they also give the pedestrian the walk sign. And then usually the light may stay on longer in a certain direction when the pedestrian has to cover a large amount of road to get across. So yeah, there's all sorts of idiosyncrasies, and of course there are even some that have intersections with more than just the 2 roads crossing at right angles. There may be a 3rd road coming in, or all sorts of crazy stuff, as you well know, because you all drive around all the time, just like everybody in the country does. So, but hopefully you'll, when you see a stoplight now, you'll be thinking about logic design. Okay, so after this, there'll be a quiz in the same folder with this video, and so I want you just to do the quiz, and as long as you get, I'll probably put 6 problems on, as long as you get 3 of the 6 problems, you'll be good to go. All right, we will see you Monday then.